So in this video, we are going to discuss titrations. So let's say you have a solution of a known volume, but you don't know its concentration. You can do a lab procedure called a titration. You can react it with another solution called a titrant and determine how much titrant is needed to complete the reaction, to completely react with all of your unknown solution. So a couple of vocabulary terms that we should be familiar with. The analyte is what you're analyzing, what you're solving the concentration of, and that is going to go into the flask. And then the titrant, what you do know the concentration of, what you're going to add to the analyte and react with it, that's going to go into the burette. So here's your basic setup. And today we're just going to focus on acid-base titrations. So you're either going to have an acid or base in the flask, and then the opposite goes into the burette. So you can have an acid-base reaction. So again, in the flask goes your analyte, and then in the burette goes your titrant. And so you're going to add just enough titrant to fully react with all the analyte that's in the flask. So there's one key point that we need to focus in on titrations that's going to allow us to figure out the concentration of our analyte, and that is called the equivalence point. This is where you have stoichiometric equal moles of your analyte and your titrant. In an acid-base reaction, remember all the coefficients in a balanced equation are going to be a 1. So essentially this is where you have equal moles of acid and base, and this only applies when you have an acid-base reaction. Essentially this is when the moles of H plus equal the moles of hydroxide being added. So during a titration, you can't visually see the equivalence point. Instead, you're going to know to stop titrating at something called the endpoint. It's very similar to the equivalence point, but it's just slightly past the equivalence point. You're just going to add just one more drop of titrant to reach that endpoint. Then you know that you're going to be at the stopping point. But because it's so similar to the equivalence point, essentially the equivalence point and endpoint are one and the same when you do a lab. But in terms of calculations, we always talk in terms of the equivalence point. Okay. Endpoint is just there to visually give us a cue to stop the reaction. That's when the reaction is going to, or the solution, I'm sorry, in the flask is going to change to a certain color so that we know, oh, hey, we are done. Let's calculate how much titrant that we used. So for indicators, you are going to want to choose an indicator whose pH it's going to change color in the range of the pH of the equivalence point. Okay, so that's how we know when to stop the titration. We're going to see a distinct color change around the equivalence point. So we're going to be asked to choose indicators sometimes. So that means we want to choose an indicator whose pKa is the pH at equivalence point. Okay, so choose an indicator whose pKa is equal to the pH of an equivalence point. And P, just keep in mind, P just means negative log. pKa would be the negative log of the Ka value of the indicator. That's how you can calculate its pKa. So for example, if you know roughly that the pH is going to be 4 at equivalence point, then you want to choose an indicator whose pKa is also 4. There's 3 main types of acid-base reactions that we typically study in this class. Strong acid and strong base that results in a neutral salt solution. And this is review. This is your net ionic equation of strong and strong. Remember from strong acid, the important player is an H+. Remember from a strong base, important player is hydroxide. They're going to make water. And remember their conjugates are spectators. And they're neutral spectators, so you end up with a neutral solution at equivalence point. But that is not the same scenario when you have a weak acid together with a strong base. Remember, weak acid, less than 100% ionization. So really, we write down the entire formula of the weak acid. We keep it whole in our net ionic equation. Strong base, though, is still hydroxide. But here's what's very important. The product of a weak acid and a strong base reaction, yes, is water, which is neutral, but is conjugate base, this A minus. So you end up making water and a basic salt. So once this reaction reaches its equivalence point, meaning you have 0 moles of the two reactants, the only thing in the flask is water and conjugate base. So, and that conjugate base is a weak base. So the pH is going to be above 7, not neutral. Okay, so not all equivalence points are going to have pHs of 7. That's only for strong and strong. When you have a weak acid and a strong base, you're going to end with conjugate base in solution. So that pH has to be basic at equivalence point. Then when you have strong acid and weak base, strong acid, okay, H plus makes it down to the net ionic equation, but that weak base, same thing. The whole weak base gets written down. And what you produce is an acidic salt in water. So at equivalence point, where your moles of acid equal your moles of base, you got 0 reactants. And the only thing you have is product. And that product is an acidic salt. Okay, this is an acidic, and again, we're ignoring the negative ion here. This positive ion behaves as an acid. It's the conjugate acid of your weak base. And so therefore, at equivalence point, your pH is going to be below 7. It's going to be an acidic solution. All right, so in our first example of a titration curve is just a graph of the pH from the start of a titration through the equivalence point and then a little bit past the equivalence point. The main thing you need to focus in on a titration curve is the equivalence point. And the titration curves are always like an S shape. So you're looking for that vertical section of that curve, and halfway up that vertical section is your equivalence point. That's where the moles of acid equal the moles of base. So if I just look here, I can tell without even looking at the picture what type of reaction we have. At equivalence point, the pH is 7. So this looks to be a neutral solution at equivalence point. So this is going to be a strong and strong reaction. But if you look at this picture, we need to specify exactly what we have here. Okay, yeah, we got HCl in the flask. That's your analyte. That we're measuring the pH of the flask solution from start to finish. So if we put a pH meter in here, yeah, at the start, before we add any titrant, the pH is going to be acidic. Okay, so here on our graph it's about 2. Then we start adding in the titrant sodium hydroxide, and our pH is going to go up, okay, because sodium hydroxide is a base. So what type of reaction do we have here? We are reacting a strong acid with a strong base. Okay. We would say strong acid titrated with strong base. Okay, that titrated with part tells us what's coming in from the burette, what we're adding. Okay, so the net ionic equation, so real quickly, okay, strong acid, H plus, together with strong base, okay, major player hydroxide, together they make water. The pH at equivalence point is going to be 7. Okay. Well, how much titrant, what volume of titrant was needed to reach that equivalence point? So looking at your graph, go to that equivalence point and then look down. What volume of titrant was needed? You needed 50 milliliters of titrant. Okay. So 50 mils of titration were needed. Okay, and our titration is sodium hydroxide. What is the concentration of the analyte? The analyte is your HCl. Okay. I want to know, what is its molarity? Well, if I know that it took 50 milliliters of sodium hydroxide, and I'm given the molarity of sodium hydroxide is 1 molar. So 1 mole per liter. And so that means, I cannot multiply those because I don't have liters of sodium hydroxide. Nice. Okay, so first of all, let's fix that. 50 milliliters need to turn into liters. So that's 0.05 liters of sodium hydroxide. Okay, now our units are going to cancel out. See how important putting in your units to your work is. Liters are going to cancel out now, and you're going to be left with moles. And so this is 0.05 moles of sodium hydroxide. Okay. Looking at your balanced equation, for every 1 mole of sodium hydroxide, there's 1 mole of hydrochloric acid reacting. So it's a 1-to-1 ratio. This is the lovely thing about acid-base reactions. Stoichiometry is always 1-to-1. So if our moles of sodium hydroxide is 0.05, therefore the moles of hydrochloric acid is also 0.05 moles. And so our 1-to-1 ratio, we can say 1 mole of HCl for every 1 mole of sodium hydroxide. Makes my math so much easier. That's 0.05 moles of HCl. So to calculate the concentration of hydrochloric acid, you're going to want to do your moles of HCl over the volume of HCl that you put into the flask. So we care about the original molarity of the hydrochloric acid that we started with at the very beginning. So it is moles of HCl over the liters of HCl initial. And so 0.05 moles of HCl were present, and the initial volume of HCl was 30 milliliters. But real quickly, move that decimal point and get to liters. So 0.03 liters. HCl has a molarity of 1.7 molar. And so there you have it. You've just determined the concentration of your analyte, the hydrochloric acid that was in the flask. In example 2 here, we have a different titration curve, and we're asked what is the reaction type, and ultimately we want to solve for the molarity, the concentration of the analyte, the stuff in the flask. So if I just look at the graph, I've got a lot of information here. The equivalence point, again, you're looking for that vertical section of the curve. Halfway up that vertical section is your equivalence point. That's where your moles of acid equal moles of base. And the pH at equivalence point here, guys, is above 7. It's hovering around 9 here. So I know that this was not strong and strong because that would produce 7. This is going to be something that is basic at the equivalence point. So you're going to have base produced at the equivalence point, and that's going to make your pH above 7. So that means, hey, I'm reacting a weak acid with a strong base because I know that weak acid is going to produce its conjugate base. And that's verified here with our picture. We have acetic acid in the flask, which is a weak acid, and you have sodium hydroxide in the burette as your titrant, and that's your strong base. So your reaction type is weak acid. It's being titrated with strong base. And so your net ionic equation, weak acid, you write down the entire formula, CH3COOH, plus strong base. All I care about is hydroxide for strong base, net ionic equations. And together, all right, that H breaks the H breaks off of the acid, joins the hydroxide, you make water. And then what's left behind is the conjugate base, CH3COO, -1. Don't forget that -1 because we always have to remove a hydrogen, but that hydrogen has a charge with it. So remember, when you create the conjugate base, we decrease by 1 hydrogen, the charge decreases by 1. And remember to always double check your nets. You want to be balanced for atoms, you want to be balanced for charge as well. So you have a -1 on the left, you got to have a total charge of -1 on the right as well. Okay. So the pH at equivalence point, according to our titration curve, is about 9. What volume of titrant was needed to reach that equivalence point? So I look here at the equivalence point and my eyeballs go down. That's 50 milliliters of titrant added. Okay. So 50 mils of the sodium hydroxide were needed. So we're going to calculate the concentration of the acetic acid. Following the same process as before, we want to know how many moles of base were required to complete this reaction. So we have 0.05 liters of sodium hydroxide, our titrant, and it has a molarity of 1 molar again, so 1 mole per liter. And so that's 0.05 moles of sodium hydroxide. Again, looking at your net ionic equation, 1-to-1 ratio. So if it's 0.05 moles of sodium hydroxide, it is 1-to-1. So the stoic is very easy. You're going to get 0.05 moles of acid. Now using that, you're going to calculate the molarity of the acid, the amount of moles divided by its original volume. That's what we were trying to figure out, the original concentration of the starting acid that was in the flask. So therefore, your concentration of your weak acid is 0.05 moles over the original volume. It was 30 milliliters, so that's 0.03 liters. This has a molarity of 1.7 molar. Okay. So number of moles over number of liters of the original acid, you've now determined the concentration of the weak acid. So some reflection questions here. How do you use a titration curve to determine the equivalence point? The equivalence point, where your moles of acid equal moles of base, is that midpoint of the vertical section. So find that vertical part of the curve, go about halfway up. That's going to be your equivalence point. So from there you can read the pH, and then from there you can read the volume of titrant that was added. Next question, why is the pH at equivalence point different for the two examples above? So if you recall example number 1, the pH at equivalence point in example 1, we had strong acid reacting with strong base. That pH was neutral at 7. But in example number 2, we were titrating a weak acid with a strong base at equivalence point, where the moles of acid equals the moles of base. The pH was basic, hovering around a 9 for this graph. Now, why are they different? It has to do with what we're producing. At equivalence point in both of these reactions, there's 0 reactants. There's 0 of the weak acid. There's 0 of the strong base left over at equivalence point. In example number 1, there's 0 strong acid, 0 strong base at equivalence point. All that is present in the solution at equivalence point are the two products. And so those two products determine the pH of the solution. For example 1, when it's strong with strong, your product is water and neutral salt. I know we didn't write it here, but remember the sodium and the chloride are spectating here, and they come from strong acid, strong base, which we know are neutral ions. So therefore, if you only have neutral salt water, you're going to have a neutral pH when you titrate strong and strong. But when you titrate weak acid with strong base, look at your net ionic equation that you wrote. You're producing water and you're producing conjugate base, acetate here in this case. And so if you have water, which is neutral, we ignore all the time, but conjugate base, we expect a basic pH at equivalence point, because remember, at equivalence point, you got 0 reactants. You've used both of your reactants in equal quantities. You got 0 of those. And the only thing present in the flask, in that solution, are the 2 products. In this case, it is water and conjugate base, so resulting in a basic solution. So in summary, your strong acid and strong base produce a neutral salt, pH is 7. Weak acid with the strong base produce a basic salt, the pH is going to be greater than 7.